Okay, so our next speaker is going to be Ajit Sapre, who's the Group President of Research and Technology for Reliant Industries. He's worked there for more than 30 years in the petroleum refining and petrochemicals business, technology development, and R&D management. His experience includes technical and managerial assignments in research, engineering, business, manufacturing, and corporate planning. Also has a strong management in technical background in catalyst development, chemical reaction engineering, optimization technologies, computer integrated manufacturing, and intellectual asset management. Also has experience in the renewable energy sector. We are so happy to have him with us today. And he's going to be talking to us about energy technology landscape, one Indian perspective. So please join me in welcoming him.
Sally, thank you very much for that kind and long introduction. I didn't realize all those things that you just said. So, good morning, ladies and gentlemen. Yeah, I must congratulate GSAIP for a decade of cutting-edge R&D. Really, the kinds of activities that you talked about this morning were really fantastic, just cutting edge. It's an honor to be invited to this annual event. I'm delighted to be here at this beautiful setting in Stanford. It's, in fact, my first time here, and it was really fantastic. I want to give you my own Indian perspective, if you will, on energy technology landscape. This is going to be a fast-paced presentation, so please bear with me. Here's an outline of my presentation. I'll quickly cover the climate and resource outlook. Most of you are quite familiar with it. I'll give you my own perspective on the role of natural gas, and I just chose biotechnology. I could have chosen solar, but I decided maybe I should talk about biotechnology today, and wind up the conversation with what I would call inclusive innovation or a Gandhian engineering. And being in Stanford, I couldn't resist but talk a little bit about my perspective on academia and industry interaction. And GSAIP clearly is one great example of how things are working well. The numbers at the top indicate the progress of this presentation, so timekeeper can keep track of what this is all about. The center of gravity of economic growth is shifting east. Volatile crude oil and climate change concerns are pushing the green agenda. Would these drivers lead to global green growth is the million-dollar question. And is it the energy security or sustainability challenge that will shape our future? That's really the question ahead of us. In my opinion, in the uncertain world, Andy talked about uncertainty. The uncertain world, what we need to worry about is the innovation. Innovation is the key to meet future global challenges. I will not dwell much on this slide. Global temperatures are on the rise, and frequency of extreme weather condition is also increasing. This is a well-accepted fact now. Melting of Arctic is in the global news. Closer to home, Himalayan glaciers are retreating at an accelerated pace. From long-term perspective, India is at risk of losing its major rivers, source of drinking water and irrigation for more than 1 billion people. So clearly, this is a great concern. Not much is happening on the political front. On climate mitigation is aptly depicted in this cartoon on the right-hand side. In my opinion, advanced countries have not done enough. And I guess there was a question about shale gas. Shale gas boom in the US, although beneficial in the near term, leaves an open question. Is it a blue bridge to green future or death of nuclear and renewables? Something for us to think about. The greenhouse gas emissions rose dramatically since 1850, as the last speakers explained to us, with accelerating industrial revolution. However, since 1850, India contributed only 2.4% to the global cumulative emissions and 4% since 1990. So table above shows for India low per capita CO2 emissions compared to the world average and significantly lower than the industrialized or advanced countries, and almost factor of 4 lower than our neighbor China. So there is a difference between China and India, and I'll talk about it as we go further. Today's CO2 emissions in a country are accounted through production and transportation of goods there. However, we need to recognize that consumers in the West are also responsible for emissions increase in the East, as East is becoming a factory to the world. Therefore, I believe consumption-based CO2 accounting may be more equitable as we look in the future. Climate negotiators have recognized the principle of common but differentiated responsibilities between the developed and developing countries. Leaving aside the politics of climate change negotiations, since the many developing countries are still early in their energy infrastructure development, they provide a fertile ground for implementing novel climate mitigation technologies and innovative infrastructure development opportunities. Example, distributed power, biofuels, etc., and some other ideas that were discussed before my previous speaker here. In a way, it's akin to India moving directly to mobile phones and skipping the landlines completely. So what are the new technologies, infrastructure opportunities that we can actually leverage? And I'll talk more about this later in my talk. Here is the composite night shot of Earth from the space shuttle. Bright lights represent prosperity, and darkness is where most of the world's population resides. Sustainability will have to account for well-being of aspiring middle class. In India, almost 50% are at the bottom of the pyramid, seeking to move up the success ladder. Here is a typical S energy consumption curve for the OECD or the rich countries as populations enjoy higher standard of living. If the remaining 83% of the world population followed this curve, we will rapidly exhaust all the resources on Earth, a clearly an unsustainable path. What we need is a more secure and responsible energy technology from the growing world that follows a more efficient path depicted by the green line on this chart, essentially a leapfrogging technology development and, more critically, deployment. And this is the challenge ahead of us for this group. And I'll talk more about this as I go further in this talk. Here is a snapshot of Indian energy demand and supply. India is a resource-poor country. Today, India imports more than 70% of the crude oil and 30% of the natural gas. With more than $80 billion revenue outgo, it's a significant impact on the national budget. Coal has a major role to play in Indian energy scenario. Coal meets about 50% of the energy demand today and will continue to be at that level in the future. So growth in coal consumption will be met by increased domestic production as well as coal imports. As you can see in that graph, we're expecting a significant increase in coal imports, and some of that may even come from the United States. As you know, shale gas is already having a big impact in reducing coal usage for power generation in the US. The good news, obviously, is that shale gas emits less carbon dioxide than coal, an immediate benefit to reduce CO2 emissions. Cheap shale gas has taken a big bite out of coal very quickly, and we do have some shale gas reserves in India, and I'll talk about that in the next slide. But clearly, this is a very rapid change, and availability of good coal in the US may supply some coal in India, and I'll talk about the coal in India and quality of it a little bit later. Technically recoverable shale gas resources in India are about 63 TCF, significantly lower than what's in China or in North America. ONGC and Schlumberger have already started exploration in India. Some of you may know my company, Reliance, is active in the US in Marcellus and other shale gas plays, and we will bring that experience back to India. As you know, extracting shale gas requires water resources, and India has a water shortage. Therefore, waterless technologies are desirable, and that's something we need to think about when we're trying to extract shale gas. Coming back to coal, Indian coal has very high ash content, typically more than 38%. The worst coal in the United States only has about 12% ash. Therefore, underground coal gasification or bioconversion of coal to synthesis natural gas provides an interesting technology opportunity. Why bring all that high ash above the ground and transport it around to the power plant? It makes no sense. There are several pilot projects are currently underway in India, and we need to progress those pilots to commercialization. We are actively engaged in this R&D today. We at Reliance are also proceeding with constructing 12 of the largest gasifiers ever built as we speak. And this is at our Jamnagar super site, the largest refinery in the world today. The cost of the syngas from these gasifiers will be significantly cheaper than imported LNG, primary driver for this project. This project will enable many other projects, such as off-gas cracker, acetic acid, and further integrating the refinery and petrochemical complex at this refinery. The world's ultra-clean, and by the way, the most energy-efficient refinery in the world will become bottomless, but more importantly, it will be future-ready for CO2 mitigation. This is consistent with our sustainability objective as articulated by our current chairman, Mr. Mukesh Ambani, and our sustainability objective are articulated in the bottom of that slide. You will not see poverty eradication in many of the corporate sustainability statements, and more about it later in my talk. But switching gears, here is a scorecard of percent of contribution to energy mix by various fuels. Obviously, the absolute amount of energy requirement has been steadily increasing with increasing energy demand. But looking in the future, really, will the biomass increase in the energy mix? Will coal usage go up? Post-Fukushima, what is the future of nuclear energy? Will natural gas remain bridge to renewable energy? In this talk, I have more questions than answers. And perhaps the GSEP scientist may have answers, and I'm really eager to learn. Let me briefly talk about nuclear in the Indian context. India's thorium-based pressurized heavy reactor technology is an advanced stage of development. India plans to start constructing a 300-megawatt thorium reactor by 2016-17 timeframe, and plans to meet 30% of its energy demand with thorium-based reactors by 2050. Throughout the human development, food, heat, light have remained essential for our well-being. Crude oil, a fossil fuel, has played a major role in the last 100-odd years. There are concerns that we will run out of this finite resource soon. The energy security concerns are driving the biofuels agenda in many countries, and I chose to speak a little bit about biofuels a little later. Here is an outlook of energy mix through 2030 by British Petroleum. Developing economies will drive energy consumption growth, accounting for 65% of the world consumption in the outer years. The good news, however, is globally energy intensity is expected to reduce and converge. This convergence is happening due to connected world and rapid diffusion of technology. Natural gas will clearly play an important role in the near future. As you know, shale gas is a game changer in the US, and it has worldwide repercussions. Huge shale gas finds and production has decoupled gas price from oil in US, the top right-hand corner picture here. US natural gas prices are under $3 a million BTU. Indian LNG marginal cost is as high as $15 a million BTU today, roughly the same as crude oil price on an energy equivalent basis. In a globally connected world, in globally connected world energy markets, the important question is, when will US start exporting LNG? In my opinion, in the immediate future, natural gas will have an impact on the transportation sector. Driven by air quality concerns, use of CNG vehicles is on the rise in India. In fact, it has helped to clean the air locally in big cities like Delhi and Mumbai. And actually, I was surprised when some of the people who are working for me said they just converted their cars, diesel cars or gas cars, to gas, natural gas that is. And I was really surprised. So with increasing natural gas availability, natural gas vehicles are likely to penetrate first in heavy-duty fleets, heavy-duty vehicles, and also in fleet applications. And one of the main reasons is with minor modifications, you can convert the existing fleet, more than 1 billion cars that are running today, on a more cleaner natural gas vehicles. And that may provide us a bridge to somewhat reduce CO2 emissions. Here is BP's forecast that one way or the other, natural gas, either through direct usage or indirectly through partial or full electric vehicles, will reduce petroleum demand. and reduced demand of refined liquid products will lead to refining capacity rationalization all over the world, and significantly here in the US. The natural gas will also play a critical role in the power sector. The electric grid is likely to see major change due to advancing smart grid technology and incentives for renewable electricity. Distributed production and distributed consumption pattern will likely emerge in the power sector. Even in India today, at the village level, mini grids are becoming quite common. They are being piloted at many places. There we gasify the agricultural waste and produce electricity for the small villages. This begs a question, and I'll come back to this again. Would we economically develop a distributed production and consumption business model for transportation fuel, especially if we are going to have increasing biofuels in our mix? India, in a way, is still an agrarian society. Agricultural sector accounts for more than 58% of the employment in the country, and more than 70% of India's population depends on biomass as its energy needs, shown in this middle picture here. Today's cooking stove is only 10% efficient. Modern stove, which is shown in this picture here, is 3 to 4 times more efficient, potentially releasing significant of biomass for conversion to biochemicals or biofuels if a proper infrastructure can be developed. As shown in the top graph, it appears that crude oil has finally caught up with the food in terms of price per unit of energy. You may not realize this, but this is kind of interesting. I did my own calculations. On a hectare of land, if you have favorable wind, you are better off investing in a windmill than energy crops, as shown in the bottom half of this cartoon. So clearly, for biofuels to succeed, we need on-purpose energy crops orders of magnitude more productive. In my opinion, I believe one way to price various feedstocks will have to be on the basis of their energy content. If you do that, the usable biomass feedstock will have to be significantly cheaper. The cartoon at the bottom of the slide depicts relative capital costs for equivalent amount of energy and number of facilities that are needed to meet the given unit of energy, if you will. With a low energy density and economies of scale, it is a challenge for biofuels to displace incumbents with existing infrastructure in at least the mature markets, but that may not be the case in developing countries. Clearly, if we can think about a distributed model, there is a good chance that we could do it. The challenge of landmass utilization is depicted in this chart. To get equivalent fuel in gallons per acre per year, at the end of the day, all the energy on Earth has originated from sun. Fossil fuels are old sun. Biomass is today's sun. And here I'm showing actually a US production well, which is not as productive at 140,000 gallons per acre per year. If I were to choose a Saudi Arabian well, probably it will go up to that wall on the other side. So it raises an interesting question. As I pointed out, in my mind, for biofuels to succeed, we need a distributed production and a distributed consumption model for transportation fuel. Today, if I think about it, we have the largest refinery in the world. It's because of the concentrated oil. We bring the oil all over there from South America, refine it in India, and sell it in the US, and still it's a very profitable business. Will that work for biofuels? Clearly not. In a likely scenario, a mix of alternative regional biofeedstocks will emerge due to scale and heterogeneity. Biomass as an energy source may make sense for countries like Australia, Brazil, USA with large land mass and relatively sparse population. For countries like India with huge population and limited land, but long coastline, we may need to look at sea to develop biomass-based fuels and chemicals. Plants convert CO2 and sunlight into biomass. Aquatic algae are significantly more efficient than land-based plants. Algae-based nutraceutical business is operational today. It's actually a fairly big business in India. And we're hoping that tools of synthetic biology, which are being applied to this whole issue, would it provide a more efficient path to produce renewable fuels and petrochemicals? Rapid advances are happening in nanobiology, as depicted in this cartoon. We also need to address the scale-up issue, or kilobiology, as I say. Perhaps we may need to develop a platform that has best features of both the land-based and aquatic plants, so which actually account for both the CO2 and the photosynthetic in an optimal way. So I believe we need to crack the fundamental limitation of photosynthesis to increase aerial productivity by orders of magnitude. I'm optimistic that advancing synthetic biology will play a critical role to retire old processes that are high cost, multi-step, and environmentally disadvantaged. We anticipate industrial biotechnology to take greater share of fine chemicals, specialty chemicals, and some biopolymers before biofuels or bulk petrochemicals. Let me illustrate this. Here is an indifference cost of making ethylene from crude or sugar-based ethanol. There's crude oil versus sugar-based ethanol. Above the line, crude is preferred. Below the line, sugar is preferred. What would be the long-term outlook of crude oil price is anybody's guess. If I knew that, I wouldn't be here. It could be lower than $100 a barrel if North America becomes a net exporter of energy and very fast. However, if developing countries' growth continues to stress the supply, then the crude oil price could go northward of $100 a barrel easily. Now, as pointed out by the previous speaker, recycle and reuse also reduces the net input of raw materials, reducing demand and lessening the pressure on pricing. Reliance is the largest polyester producer in the world today. In India, the bottle recycling, the plastic bottles that you have for your water, is very successful. In fact, we have perhaps the most successful rate in the world, at 70%, compared to, say, US, which is at 30% recyclability. Actually, what happens here is that it provides income to unskilled labor and improve their quality of life. Actually, that's what is driving this whole business of recycling, as shown in this cartoon here. And so let me talk a bit more about the underprivileged and why the poverty eradication is at the heart of what we need to do if we want to become sustainable. Here's another cartoon, the ethical question. Must the poor go hungry just so the rich can drive? Actually, it's just recently from The Guardian in the August issue. The first generation biofuels certainly have an impact on the food prices. In fact, in the US, I would say it's not the energy policy, but the agricultural policy that became the energy policy. 40% of US corn is directed to run cars. With every 1% increase in food prices, 16 million people go hungry. Certainly, the focus of biofuels need to be maybe third or fourth or fifth generation, clearly not on what we're doing today. So coming from India, I must quote one of our founding fathers, Mahatma Gandhi, and that probably may give us a clue on what is it that one path that we could choose. He said, Earth has enough for everybody's needs, but not enough for anybody's greed. And poverty is the worst form of violence. In Reliance, we have a fundamental belief that sustainability can be achieved by poverty eradication and meeting future aspirations of underprivileged. It also means that not only to have innovation and passion, but compassion. It simply means more from less for more and more. So this is all about efficiency and frugality of doing things. And I call that a Gandhian engineering or inclusive innovation. To meet the aspirations of population all over the world, we need to make products affordable to the poor without compromising quality so that even rich will desire these products. If we achieve that goal, we'll have done something really wonderful. So Gandhian engineering is as much needed by the rich as by the poor because ultimately it affects the entire mankind as we run out of non-renewable resources. Two examples of Gandhian engineering are given here. India has the cheapest cell phone service in the world with more than 600 million customers, and growing rapidly. Similarly, I've given here an example of Tata Nano, which represents the cheapest car at $2,000 with all the features, including air conditioning, that you will see. So the whole idea here is that if we can produce products which do not compromise on quality, but can be done at a very low cost, then that will probably help us to achieve the goal of sustainability while meeting the aspirations of growing middle class. I'll give a few other examples. Biogas is actually an Indian initiative. Maybe you can think about it as a distributed energy. There are many biogas plants in India. Actually, it started in 1897, the first very plant on digesting waste. And this actually is very common in Indian villages. But the beauty is it's now spreading to cities. In fact, Mumbai, where I come from, is installing a very large biogas plant to take the waste and convert that to useful energy. So rural innovations are now spreading to the cities as well. India as a country has taken a challenging goal of installing 20 gigawatt of solar power by 2022. And that will certainly improve the quality of life for many in the Indian villages. Here I'm showing a few examples. In fact, Reliance is in the solar business. So we're showing here the solar mobile chargers, the street lights, the water purifier, pumps, and overall, for people to enjoy electricity, if you will. And here's another classical example of a Gandhian engineering. You may think it's funny, but it's real. And this is actually happening in a lot of villages in India as well. This is a mix of modern and traditional technology. It's a classic example of what I would call a Gandhian engineering. It's a 4-minute of pedaling. It gives 4 hours of light. And certainly, this is a ray of hope for many in our villages. Let me switch gears and talk about challenges with energy technologies. So coming back to the modern energy that the previous speaker talked about. Energy technology deployment clock speeds are measured in decades, as shown in this graph. Materiality in this graph actually corresponds to 1% of the energy mix. And if you think about it, most of our today's energy has taken at least 3 decades before it reached any level of materiality. So we cannot avoid the question of deployment. And all technologies go through this initial exponential phase, followed by a linear phase, if you will. So we certainly need to accelerate this particular clock speed. 3 decades is not acceptable. We need to do it less than a decade in terms of deploying technologies if you want to meet future challenges. And the challenge before this community is, can we do it? Can we do the deployment very fast of new technologies on a scale of a decade, not 3 decades? And I believe it can be done. Being here in the Silicon Valley, I could not avoid but put this cartoon. There's one important difference that we need to recognize between IT and energy technologies. As discussed in the previous chart, energy technologies characteristically have a slow clock speed for both technology development, but more importantly, for deployment. Investments are very high in the energy sector, and they're typically irreversible. And that's a big contrast compared to IT and communications. IT and communications technologies, both the technology development is fast and deployment is even more rapid. Just think about it, a new version of Windows can be downloaded by millions in days. So deployment is of order of weeks at best, not decades. So that's a big difference. And the real question is, would the biotechnology materially change the energy paradigm? Would it accelerate the clock speed of development and deployment and provide more secure and responsible energy technology for the growing world? Perhaps, as I said, a distributed production and distributed consumption model, if it can be developed, we have a hope. And I think that's what we need to think about. We need to change the paradigm by which we produce energy and we supply energy. Let me change gears. Since I'm at Stanford, I felt like maybe I should give one perspective on academia and industry interaction. And this is my personal perspective, and perhaps some of you may not think this makes sense. And GSEP is probably clearly an exception. But if I think about it, over the last 100 years, the structure of scientific enterprise evolved as depicted in this simple cartoon. A government gave money to academia. Professors worked on problems of societal importance. Some of them in the process became quite famous, but they also produced a byproduct of skilled manpower. Most of them became professors, but some did go to industry. And when industry had an R&D, a central R&D function, if you will, then there was a capacity in the industry to understand the science and efficiently translate that science to commercial activity because we had skilled resources. And we knew what is it that we need to realistically take out of the science, convert it into a technology, and commercialize. Since the fall of the Berlin Wall, and perhaps by Bayh-Dole Act in the US and similar acts in other countries, including India, which essentially allows private use of public money and concurrently a disappearance of big R&D functions in the industry where we lost capacity, which are actually disappearing in most part of the world, especially in the energy and the chemical industry, the world has changed. Today, we see most universities in the business of startups, backed by venture capital and private equity. This has been a successful model for fast development and fast deployment technologies, such as IT and communications. But I worry whether this is going to work for energy technologies. In industry today, we are sprinkling money across many startups, hoping some of them will succeed. It's a typical portfolio play that any MBA will tell you. But I still wonder whether that's what's going to solve our problem and the scale at which we need to do. Today we are taking some of the successful starts of integrating by acquisition, but I worry about the capacity of an industry to do this efficiently. Now let's look at the scorecard of VC and private equity for the clean tech industry. VC and private equity investments in the clean tech have not done that well. Actually, clean tech returns are negative, as shown in this picture here. And if you look at the performance in 2012 year to date, it's all negative. Dates are hard to come by. VCPE, in my opinion, lacks the appetite for scale-up and patience for returns for slow development and deployment technologies. So there may be a mirage that a startup is actually what innovation is all about. That's not sufficient in my mind. It's deployment that what really matters. And so really it begs the question, what is the right investment model? I really have no answers. Perhaps, as the previous speaker talked about, more governmental support for long-term development and with appropriate management of IP. And certainly the strategic investors with an appetite for what I would call a patience capital is what is needed for us to succeed. I believe perhaps what we need to derive is the maximum value from all available knowledge. We know how to derive value from economies of scale and scope. Reliance is a prime example of that in India. In just less than 30 years, we built a $80 billion business. So we know how to deal with scale and scope. The real question for all of us is how do we exploit collective wisdom and benefit from economies of learning, doing things smarter. We need to build on collective connected ingenuity in today's boundaryless world. Today's scientific enterprise, simply as I discussed before, a university, a startup, and then industry, is akin to a relay race in my mind. There's a good chance the baton may not get handed over to the next runner. What we perhaps need is a unison action of a tango. I don't know what it really means, but perhaps a closer public-private partnerships throughout the entire pipeline from discovery to deployment across the national boundaries. So clearly, I must compliment GSEP for what you have done, but what I'm saying here is that we need to go much beyond at a much larger scale, and we need more of these GSEPs in an integrated way across the world. And actually, if you think about it, organizing scientific research on the scale of big operatic and theoretical production is still something new in science and engineering. The fine arts somehow have figured out how to work together. We in science and engineering need to learn from that and figure out if we need to solve the problem that we are confronting ahead of us. So to sum up, this is my last slide. I started in talking about poverty eradication and kind of proposed a Gandhian engineering, which talks about actually frugality and efficiency. In my mind, the inclusive innovation is simple. It is a product of creativity and execution. We in industry are all about execution, as it talks about raw material flexibility, CapEx efficiency, OpEx efficiency, so on and so forth. You in the university are actually, you excel in creativity, and GSAP is clearly a prime example of that. And obviously, we need to tango. I mean, to tango to efficiently meet the energy needs in the resource-constrained world. In my opinion, our collective mandate is science for solution, technology for transformation, and really innovation for impact. And so I would like to end with another quote from Mahatma Gandhi. It says, "I would prize every invention of science made for the benefit of all." In Reliance, we believe growth is life.
I see someone back there, if we could get the mic back there, and then we'll move up to you next.
Hi, I'm Elton Sherwin. I'm a venture capitalist. I was particularly interested in your last few slides. I'm also the author of Addicted to Energy. It's very hard to disagree with anything that you said in your excellent presentation. I thought it was particularly humbling to hear an industrialist talk about poverty eradication. I'm trying to think of when the last time I heard an American industrialist talk about poverty eradication. I'm not sure that I ever have. Might I ask you one tough question? If we get, I think that was a nod.
Sure, I mean, anything goes, I mean, certainly.
If we get everything right and we get coal wrong, we really change the planet irreparably. What do you think it's going to take to get sequestration? And as you said in your presentation, India cannot get off of coal. America might be able to abandon coal, but you can't. What will it take to get sequestration widely adopted in India, China, Russia, Poland, but start just with India?
Yeah, actually, I was hoping the shale gas probably will help us in the near term. But obviously, from a coal perspective, I think I did allude to, why bring all that coal up? I mean, why not convert the coal to syngas, either bio-route or underground coal gasification itself? And that itself actually creates an opportunity for carbon capture and sequestration. Now, from a technology perspective, I mean, if you think about when I said the Jamnagar refinery is ready for CO2 mitigation, since we put these gasifiers, the world's largest gasifiers ever built at one single site, we are going to take that CO2 and going to do a few things with it. Initially, obviously, it will be enhanced oil recovery just offshore of the Indian west coast. But then it will be ready for sequestration. Our E&P group is quite active in looking at opportunities for sequestration, if you will. But certainly the technology is something, we've been doing it at Sleipner for almost 20 years. Now, can we do it at a larger scale? That's the question. And perhaps some of the scientists in GSIP could give us a warm and fuzzy feeling that it is safe and you can do it. The question really is the cost. If you don't price the carbon, it's very hard to figure out how would carbon capture and sequestration happen all by itself. And something you have to reflect yourself and say, what is it that we are doing here in order to help, A, improve the efficiency, B, increase the probability of success, and what sort of partnerships can we build across that will allow us to make this thing happen. And I guarantee you, no VC and PE will put money into sequestration today.
Okay, all right. Yes, you.
I'm Evan Hughes, Biomass and Geothermal. My question is asking you to comment on your slides talking about the 1 decade of change to a major industry in communications and computers, IT, versus the 3 or 4 decades, say, for energy transformation. I agree we need energy transformation faster than 3 or 4 decades to meet the global problems, as we saw. I think you are suggesting that in India, there are places where energy hardly exists, just like the potential for communications and computers that we saw hardly existed before that industry grew so big. I think you're looking at biotechnology to somehow fill that gap, but could you comment on whether that is your idea, that we're now trying to expand energy to where it does not exist, just like we expanded information technology and communications where it did not exist?
No, that's an excellent question. Actually, the idea I was trying to promote was this whole thing about distributed production and distributed consumption. I just happened to choose biotechnology. I could have just talking about PV or something else. And the biotechnology has a relevance in India just because of being an agrarian society. We have fairly large biomass production if we can efficiently allocate it. And so, I mean, if you think about it, you know, the IT and communications, we talk about viral, right? Things go viral. Here, can the viruses be made more efficient? And can I do this locally, where you produce energy locally and you consume energy locally? So there's not a big burden on building a huge infrastructure to transport electricity, transport liquid fuels. And that model has happened in a few villages for electricity where biomass is collected and gasified, and just the mini grids are used locally. And the point I was trying to make about IT and communications, clearly the IT and communications has helped the society. And the difference there is that it takes a lot less capital to do something in IT. Now, how do we get to a model whereby you don't need trillions of dollars of investment in energy sector? Can you do it locally in a small scale? And that's what the Gandhian engineering is all about, doing it frugally and doing it efficiently. So it doesn't consume a lot of resources, but still meets the end need. Now, I don't have all the answers, but I think that's something what we need to think about. And that's something we've been thinking about and saying, how do you do it in a very small scale locally, where you have the local production and local consumption? And biomass is something available locally everywhere. So is PV. I mean, India is blessed with sunlight. You know, could we have more efficient solar locally produced and meeting the needs, and obviously and far more efficiently?
Okay, well, thank you so much.